All right, well, hello, and we are going to jump on into the 8th chapter, which deals with right triangles. The main objectives in this chapter are to talk about the difference or to determine the geometric mean between two numbers, to state and apply the relationship that exists when the altitude is drawn to the hypotenuse of a right triangle. We're going to state and apply a Pythagorean theorem, converse of the Pythagorean theorem, and how it relates to obtuse and acute triangles, and then determine the lengths of two sides of a 45, 45, 90 degree or a 30, 60, 90 triangle when the length of the third side is known. So we'll first of all start to talk about similarity in right triangles 8-1. So when we have a proportion, a over x equals y over b, the terms in red are called the means. And the other numbers, the a and the b, would be called the extremes. So in order to find what are called what's called the geometric mean between two numbers, is you set up a proportion a over x equals x over b. And x would then be called the geometric mean. And so all you have to do is multiply a times b, and that equals x squared, so that x, the geometric mean, is the square root of the product of those two numbers. So all you have to do is know those two numbers, multiply them together, and take the square root. So if you want the geometric mean between 5 and 11, we multiply 5 times 11 and take the square root. Okay, pretty straightforward there. The first theorem in this section has to do with the altitude, which is drawn to the hypotenuse of a right triangle. So what happens is you have two other triangles that are formed when you draw an altitude from the right angle to the opposite side, which is called the hypotenuse. So when that happens, the other two triangles are going to be similar to the original triangle and to each other. So in this case, our triangle ACB, which is the one we started with, ACB, is going to be similar to ANC and CNB. All right, so it's important to get these similarities matched up properly. And one way to do that is to just split the drawing up. And then we've got our big triangle out here. And let's label everything. This is C, A, and B. This one over here is CAN, and over here is N, C, and B. So you notice that in the big triangle, this is the right angle. And the one on the left, this is the right angle. And the one on the right, this one is the right angle. And we have kind of like a short side and a long side of each one. So when we're doing similarities, we want to compare the short side to the short side, et cetera, et cetera. So on this first triangle, our shortest side is AN. And the second triangle, the shortest side is CN. And then on the third side, it is AC. All right, so if we just fill in, the only thing that's missing in each of these triangles is the letter B. At least on this, on this third triangle, the B is missing. On the second triangle, the the B is missing. On the first triangle, the C is missing. So that gives you your similarity arrangement between those three triangles. And we got to make sure everything is in the right order. And we can do the proof for that by using the AA similarity postulate, because we'll start with having that angle B is congruent to angle B. and then angle C is congruent to angle N, so that makes these two similar. And then if we did that on this side, we would have angle C congruent to angle C, and the right angles congruent. And if we did these two, it would be angle A and angle C. So in each pair of triangles, we have AA similarity. And that proves that all these are similar to each other. Okay, so we're going to look at two corollaries that deal with this situation where you have an altitude drawn to the hypotenuse in a right triangle. So we're going to come up with some names for these different segments that are created, such as segment, side, leg, and hypotenuse. So we're referring to that as the length of the segment rather than the segment itself. So corollary 1, when the altitude is drawn to the hypotenuse of the right triangle, the length of the altitude is the geometric mean between the segments of the hypotenuse. So what that says is that this altitude Cn is equal to An times Nb square root. So if we're wanting to find these two segments here, the geometric mean will give us Cn. Corollary 2, when the altitude is drawn to the hypotenuse, each leg is the geometric mean between the hypotenuse and the segment of the hypotenuse that is adjacent to that leg. So what does that mean? So if we've got the altitude drawn here, each leg is the geometric mean. So like, for example, AC is the geometric mean between the hypotenuse, Cn, and the segment of the hypotenuse that is adjacent to that leg. Okay, so in this case, let's see if I got this right here. Okay, so the altitude, each leg, so like this leg AC, is the geometric mean between Cn, between the hypotenuse, which is AB, and the segment of the hypotenuse that is adjacent to that leg. So that would be AN times AN, geometric mean. So that says that the geometric AC, this segment, is equal to the geometric mean of the hypotenuse AB and the segment AN that is closest to that leg. Same thing over here. We could say that CB is equal to AB, or the geometric mean between AB and NB. So let's write that out. BC, geometric mean between AB and BN. And you can prove that by doing, because we know they're similar, then the ratios of corresponding sides are equal. Okay, so when we're working with geometric means, we're sometimes going to just be working with radicals. And so if we have a radical, we want to write it in the simplest form. And what simplest form means is that there's no perfect square factor other than 1 under the radical sign. No fraction is under the radical sign, and no fraction has a radical in its denominator. So, for example, 5 square root 18, we've got a perfect square of 9 that we can pull out of the 18. And so this would become 5 times the square root of 9 times the square root of 2. Square root of 9 is a perfect square, so that's 3. 5 times 3 times square root of 2, which is 15 square root of 2. This square root 3 over 2, a couple different ways that we could do this. One is to split it up into square root 3 over square root 2, and then we rationalize the denominator by multiplying top and bottom by square root 2. Get square root 6 over square root 4. Square root 4 is just 2, and we have square root 6 over 2. And then C is the same thing, that we just need to, and when we have a radical in the denominator, multiply top and bottom by that radical to get rid of it. All right, and then example 4 is just an example of finding the values of w, x, y, and z. And here's one where you have the altitude drawn to the hypotenuse of this bigger right triangle. So if we're using corollary 2, that would tell us that the ratio of these two sides, 18, which is the hypotenuse, over 6, which is one of the legs, is the same as 6, or I'm sorry, 6 over W. That would be the W would be the segment adjacent. It's the adjacent segment. And 6 would be the hypotenuse of the other triangle. So when you multiply these out, 18 over 6 equals 6 over W. 18W equals 36, and W equals 2. And then for the finding Y, we use corollary 1, and that just says 16 over Y equals Y over 2, because we already found W was equal to 2. So now we know the the length of the two segments created by putting the altitude to the hypotenuse. So then we would just take 16, which is this ratio, or this length, over Y equals Y over 2. And that's the geometric mean between the 18 and the 2, 16 and the 2, excuse me. So it's the square root of 32 and the simplifies to 4 square root 2. And then for the Z part, we do a similar situation as the first part of the problem, where we do corollary 2. 18 over Z equals Z over 16. And then we end up with 12 square root 2. Okay, so go ahead and work the classroom exercises here. And if you have any questions, we will go over those.